Welcome to next lecture. In the previous lecture, we discussed half-wave rectifier circuits with diode based and SCR based. At the end of the previous lecture, we discussed what is the problem with the half-wave rectifier circuit. That is, source current will have DC component. Because of that, there is a possibility for source transformer to saturate. Therefore, they are not preferable for high power applications. In order to go for high power applications, we need to prefer full wave rectifier circuits. Okay. So first let us start single phase full wave phase controlled rectifier, and in that the first configuration is center tap configuration. Okay. Now this is the circuit diagram. This is a center tap arrangement. Now here, for example, let us consider the source voltage VAO is equal to Vm sin omega t. So that due to the center tap transformer property, VBO will have 180 degree out of phase. So VBO can be represented as minus Vm sin omega t. Okay. And if you look into a waveform pattern of these two equations, here I just plotted quickly for reference. VAO, the blue color sinusoidal, is a reference waveform, and VBO, the red color sinusoidal, is mirror image of VAO, which is 180 degree out of phase. Okay. So this is a pi and this is a 2 pi, and here it is 3 pi. Now let us look into the circuit diagram. In this particular circuit, there are two SCRs named as T1 and T2. Now observe carefully here, the load is represented something different comparing with the full wave half wave rectifier circuits. So in full wave rectifier circuits, before starting the analysis, first we will consider few assumptions. Okay. So after this, we will relax those assumptions and then we will discuss that separately. So what is that assumption? Now if you recollect from our previous half wave rectifier circuit, in case of inductive load, output current waveform, what we noticed that it contains sinusoidal and exponentially decaying component. Okay. So because of half wave rectifier action, it has only one pulse for one cycle, right? Suppose when you consider full wave rectifier circuit, in one cycle itself we may have two pulses. It will be like this. Now in this particular waveform pattern, this difference, peak to peak difference, is represented with the symbol delta I naught, where that delta I naught is called peak to peak ripple current in the output, right? So what is the assumption here is, suppose if the load inductance, follow carefully, suppose if the load inductance is very large, in other words, if the load inductance is sufficiently large, then what will happen? This delta I naught will be very small. Delta I naught will be very small, so that output current waveform can be approximately treated as a constant line. Okay. When delta I naught is very small, we can treat I naught waveform is approximately constant. Under what condition? If load inductance is sufficiently large, if load inductance is sufficiently large, then we can say that delta I naught is approximately 0. In other words, ripple free load current. Okay, ripple free load current. Under that conditions, we can write that output current is constant. Okay, output current is a constant. In other words, as output current is constant means, look into the circuit diagram, load current will always flows. Load current will always flows. That means load current will continuously flows. So in such cases, we can refer that the circuit is operating with continuous conduction. Okay, the circuit is operating with the continuous conduction. Under these conditions, we can also refer that load is current stiff load. Load is a current stiff load. So these type of conditions or assumptions will be possible only for RL or RLE loads. These type of conditions will be possible only for either RL or RLE loads with sufficiently large inductance. Therefore, observe carefully, the load is represented with a rectangular box. The reason is the same, whatever explanation we will give it now, the same explanation is applicable for either RL load or RLE load. Okay. Now, one more point. When the load current is constant, you can say that load current will always flows from X to O. Under what conditions that will be possible, we will see now. Now see here, T1 device is connected to source terminal A. Therefore, we can say T1 will be forward biased whenever VAO is more positive. As T2 is connected to source terminal B, we can say T2 will be forward biased whenever source VBO is more positive. Now, if you look into the source voltage waveform, we can understand here VAO is more positive from 0 to pi. Okay. Therefore, we should give gate current to T1 device between 0 to pi, that is at omega t is equal to alpha, T1 device should be triggered. So here G1 symbol is used to represent gate current given for T1 device. Next, pi to 2 pi VBO is positive. Okay, pi to 2 pi VBO is positive. Therefore, we should give firing angle to T2 between pi and 2 pi, that is at omega t is equal to pi plus alpha. So at pi plus alpha, gate current is given to second device, that is T2. So this is a symmetric triggering sequence. Therefore, in the next cycle, T1 can be triggered at 2 pi plus alpha. Okay, this is what the triggering sequence. Now, what is important point to understand here, T1 device is triggered at alpha. Therefore, T1 will be in conduction from alpha to pi, no doubt about it. But pi to pi plus alpha, source voltage is going to be negative. In that condition, for example, we may feel that T1 may turn off, but T1 will not turn off here because load is assumed to be a large inductive load. So what I can say here, under these assumptions, I can draw simply output current is equal to a constant magnitude of capital I0. Okay, output current is equal to a constant magnitude of I0. So because of that heavy inductive load property, suppose if T1 stops conduction at pi, T2 starts after pi plus alpha, between pi and pi plus alpha, it will not be any conduction. Okay, but in case of heavy inductive load, such a scenario is not possible. Therefore, when you are talking about continuous conduction load or current stiff load, now remember one point, SCRs will turn off in two situations. Okay, One is, if one device is a started conduction, that device will be turned off before starting the next device if at all this current comes to 0, that device current comes to 0. But in case of constant current load, current will not comes to 0. So that rule is overruled in this particular case. So whenever there is a constant current load, under what conditions devices will be turned off? Once the device has started conduction, that is at alpha, this particular device will turn off when the next device started conduction, that is at pi plus alpha. So again I am repeating, SCRs will be turned off in two situations. One is either the current has to reaches to 0 or some other device should take up that conduction. In case of constant current load, current comes to 0 is not possible. Hence, once the device is started conduction, that particular device will turn off whenever the next device started conduction. Okay. Therefore, we can say conduction interval for T1 is from alpha to pi plus alpha. Similarly, conduction interval for T2 is from pi plus alpha to next device started conduction, that is at 2 pi plus alpha. So with these conduction sequences or conduction intervals of individual devices, before drawing the waveform, first let us look into equivalent circuit diagrams. Now the equivalent circuits are, look into this circuit diagram. Suppose when T1 is on, what is the interval for that? Alpha to pi plus alpha. So we can draw the equivalent circuit something like this. VAO I can represent with one source symbol like this. So this is terminal A, this is O, and this is terminal B. Okay. Now T1 device is on. So what I can do here, I can close that T1 device. T2 device, what happened to T2 device, we'll see it. Okay. And this is about the load. This is about the load. So here this terminal is X, right? Therefore, what is output voltage in this particular scenario? Okay. So X terminal is connected to source terminal A. X terminal is connected to source terminal A. Therefore, I can write here V0, which is measured across X and O, will be equal to VAO. Okay. So in this first half cycle, that means alpha to pi plus alpha, output voltage V0 is equal to VAO. Therefore, let us put this conclusion in the waveform. What is that? V0, that is from alpha to pi plus alpha, alpha to pi plus alpha, output voltage is same as VAO. Okay. So if you look into the source voltage waveform from alpha to pi plus alpha, if you take VAO blue color sinusoidal and if you draw here, it will be something like this. Okay. VAO waveform plot will be like this. So alpha to pi plus alpha VAO, the blue color sinusoidal plot will be like this. Okay. So in this interval, what is the device in conduction? T1 device is in conduction, right? T1 device is in conduction. Next, at pi plus alpha, T2 is triggered. So what is the equivalent circuit? Let us see that. That is in the second half. Okay. So this is a one source VAO and this is a second source, that is VBO. Now T2 device is turned on, and what happens to T1, we'll see that next. Okay. This is T2 device. So here source terminal, this is A, this is O, and this is a B. These are sinusoidal source. So load is given here, and this is x, okay. And this is x. Now V naught, that is measured across the terminals x and O. V naught, that is measured across x and O. So what is V naught? When when T2 is turned on, load voltage, see, under any conditions load voltage is measured between x and O. So what is VXO? That is equal to VBO. What is the reason for this? Because terminal X is connected to source terminal B, right? So as long as T2 device is in conduction, output voltage is equal to VBO. So let us put that in the waveform. So pi plus alpha to 2 pi plus alpha, output voltage will be same as that of VBO, where VBO is red color sinusoidal waveform. Therefore, pi plus alpha to 2 pi plus alpha, V naught is the same as that of VBO. Okay. So pi plus alpha to 2 pi plus alpha, what is the device that is in conduction? T2 device is in conduction. In the similar lines, the next cycle again T1 will be in forward bias, and hence output voltage will be followed by this blue color sinusoidal waveform. Another important point here is 2 pi to 2 pi plus alpha, this red pulse, 2 pi to 2 pi plus alpha is the same as that of 0 to alpha. So I can draw here red color pulse, that is a T2 conduction. Okay, that is T2 conduction. Now this is about output voltage waveform for midpoint converter. Now here we need to justify the line commutation process. Follow carefully. Okay. Now just look into this equivalent circuit diagram. Look into this equivalent circuit diagram. When T1 is on, this is a T1 device, what is voltage across T2? What is voltage across T2? That is simply nothing but anode to cathode voltage. So when T1 is on, we can say that cathode terminal of T2, that is K, is connected to source terminal A. So how can you write voltage across T2 here? That is VBA. That is VBA. So how can you define VBA? VBO minus VAO. Whenever you are writing voltage across two terminals, okay, voltage at first terminal with respect to reference minus voltage at second terminal with respect to reference, you can write it as VBO minus VAO. So what is this value? Minus 2Vm sin omega t. So important point here, that is when T1 is on, T2 voltage is negative. That means T2 is a reverse bias. Next, if you look into the current direction, load current will flow in this direction, that is through T1. That is through T1. So in this particular interval, what is the current flowing through T2 device? Current flowing through T2 device is equal to 0. Now observe carefully. In order to turn off SCR, zero current and reverse voltage are the necessary conditions. Therefore, we can say these two conditions are created due to source property of the input. Okay. So therefore, we can say that the scheme of commutation is referred as line or natural commutation. In the similar line, we need to justify how this commutation is taking place in the second circuit. So here T2 is on. Now let us look into what is voltage across T1 device, that is anode with respect to cathode. So under this condition, VT1 is equal to VAB. VT1 is equal to VAB. So what is VAB now? VAO minus VBO. This is equal to 2Vm sin omega t. Okay. 2Vm sin omega t. Now the question is, everyone think yourself, is it positive or negative? This value is negative. Okay. This value is negative. How it is? Let us see. Whenever T2 is turned on, what is the angle? Pi plus alpha. Yet pi plus alpha, T1 is subjecting to VAO minus VBO. Now look into the waveform. Yet pi plus alpha, what is VAO value? That is negative. And what is VBO value? That is positive. Negative value minus positive will give you negative. And hence, yet pi plus alpha, whenever T2 is triggered, T1 voltage is negative. Hence, it is a reverse biased. Okay. Now, if you look into the current path, load current will flow through T2 device like this. Load current will flow through T2 device like this. Therefore, what is current flowing through T1 device? That is 0. Okay. Now, just as a high level, one common conclusion, we can write it like this. In single phase midpoint converter, in single phase midpoint converter, if one device is on, voltage across other device is negative and current through other device is 0. Other device is a 0. And hence the scheme of commutation is referred as natural commutation. Okay. The scheme of commutation is referred as a natural commutation. Now, using these conclusions, let us draw voltage across T1 waveform. Okay. Let us draw voltage across T1 waveform. So, T1 is conducting from alpha to pi plus alpha. Okay. Therefore, voltage across T1 is 0 from alpha to pi plus alpha. Next, from pi plus alpha onwards, okay, what is voltage across T2? That is minus 2Vm sin omega t. So, you can draw minus 2Vm means you can readily start from the negative side. Now, 2 pi to 2 pi plus alpha, T1 condition is in forward blocking state. T1 condition is in forward blocking state. Therefore, I can say here this particular voltage is 2Vm sin alpha. 2Vm sin alpha. And this peak value is minus Vm. This peak value is a minus Vm. Okay. This is a minus 2Vm sin omega t plot. So this peak value is a minus 2Vm, right? Now from this waveform, we can find out or we can represent circuit turn off time interval. From where to where circuit turn off time for T1 device? T1 current is 0 at pi plus alpha. If you look into voltage, that is a reverse voltage due to external circuit, that is at 2 pi, it is 0. Therefore, circuit turn off time can be defined from pi plus alpha to 2 pi. Pi plus alpha to 2 pi. Okay. Now let us write down these conclusions at one place. Peak inverse voltage is equal to 2 Vm. Circuit turn off time is equal to pi minus alpha, or Tc is equal to pi minus alpha divided by omega in second. Okay, Tc is equal to pi minus alpha divided by omega in second, right? Now in the similar way, let us draw voltage across T2. Voltage across T2, now see here, from 0 to alpha, T2 is in conduction, hence I can draw this value is equal to 0. Next, alpha to 5 plus alpha, just now we calculated, that was 2 Vm sin omega t, and we also justified that that value was negative, hence it will start from the negative side and it will be like this. Okay, so from this waveform we can quickly calculate this value is minus 2 Vm, hence in this case again peak inverse voltage we will get it as 2 Vm. Next, circuit turn off time. Okay, circuit turn off time is measured from alpha to pi. Circuit turn off time is measured from alpha to pi. Therefore, this interval is pi minus alpha. Same conclusion as of a T1 device also. Okay, therefore, PIV is equal to 2 Vm. Circuit turn off time is equal to pi minus alpha. Okay, or Tc is equal to pi minus alpha by omega. This is applicable for second device as well. Now, from this waveforms, so with this waveforms are completed for midpoint converter. From this V0 waveform, let us calculate average output voltage. Average output voltage, that is V0 is equal to 1 by periodicity. So for this waveform, what is the periodicity? That is pi. Therefore 1 by pi integration. Now see the blue color sinusoidal, what are the limits for that? Alpha to pi plus alpha. Therefore alpha to pi plus alpha. What is the equation for blue color sinusoidal? That is VAO. VAO equation is Vm sin omega t. So we can write here Vm by pi integration for sin omega t is minus cos omega t, limits from alpha to pi plus alpha. Okay, so by simplifying this we will get V0 is equal to 2 Vm by pi cos alpha. Okay, V0 is equal to 2 Vm by pi cos alpha. After that, power delivered to the load is equal to V0 multiplied with I0. So this is about single phase midpoint converter analysis. In this circuit there are few drawbacks. What are that drawbacks? Let us list out here. Drawbacks of this particular circuit. Okay, so the first drawback is it requires midpoint, that means center tap transformer. Okay, it requires center tap transformer. What is the drawback with the center tap transformer going forward? You will understand. Now the second drawback is PIV rating is equal to twice the source voltage peak value. Because of this, device's voltage rating will be double the source voltage rating. Suppose if the source voltage is 100 volt, you have to choose the devices of 200 volt. Okay, therefore these are the two limitations of midpoint converter, these two limitations can be overcome in the next configuration, that is bridge configuration. Now let us look into the next circuit, that is bridge configuration. In this circuit, basically whatever the drawbacks addressed in the midpoint converter, those will be addressed. Okay, follow carefully. This is one of the important circuit in the rectifiers chapter. This circuit is also called single phase fully controlled rectifier or single phase full converter. Okay. Now here in this bridge circuit, this is what the bridge circuit, the upper half devices can be numbered with odd numbers T1, T3, and the lower half devices are numbered with T4 and T2. The reason in having a numbering like this we'll discuss later. Okay, in three-phase rectifier I will explain in detail. For time being, just take this number sequence as a standard sequence. Now, source terminals, let us take A and B, where voltage across AB can be represented with Vm sin omega t. Load terminals can be represented with X and Y. Output voltage can be measured across X and Y terminals. Now in this circuit again, the load is represented with a rectangular box. As we discussed earlier, it implies that load current is a constant. So what we will do, we will finish constant load current discussion in full wave rectifier circuits first completely. Okay. After then, we'll take up a second scenario, that is a discontinuous conduction. Next, the reference direction for source current can be taken like this. We'll talk about it later. So just at this moment, take that source current reference direction like that. Now VAB is equal to Vm sin omega t. Here I quickly plotted source voltage VAB, which is a blue color sinusoidal like that. Okay, and the red color sinusoidal is simply VBA. VBA is just mirror image of VAB. Now remember carefully, in earlier midpoint converter there was a second winding to create that VBO, but here such a scenario was not there. However, VBA is plotted. VBA purpose is just to have a reference. So going forward, if you get conclusions VAB, then we will follow blue color sinusoidal. If you get conclusions VBA, then we will follow red color sinusoidal. Purpose of VBA is just for reference. Okay. Next, now let us look into this circuit diagram again. So here basic concept is upper half devices. Observe carefully here, cathodes for these two devices are connected at a common point. Similarly, for the lower half devices, anodes of these two devices are connected at common points. Okay. So what we can say here, upper half devices T1 and T3 are in common cathode configuration. Okay, upper half devices T1 and T3 are in common cathode configuration. Lower half devices T4 and T2 are in common anode configuration. T4 and T2 are in common anode configuration. Now, in the previous lecture, we discussed the basic properties of common cathode and common anode configurations. Okay, by using that, what we can say, T1 and T3 devices, these two devices are connected to two terminals A and B. Therefore, we can say that T1 will forward bias when potential at terminal A is greater than potential at terminal B. That means A to B voltage is positive. In the similar lines, if you look into common anode configuration, lower half device, T2 will forward bias when potential at B is less than potential at A. So we can say here VBA is negative. Okay. So what do you mean by that? Whether VAB is positive or VBA is a negative. These two conditions will be true. Okay. So let us look into the waveform. VAB is positive and VBA is negative from 0 to pi. Therefore, we in the sense external gate drive circuit should supply gate current pulse for T1 and T2 devices pair here, okay, not a single device, for a pair of devices. What is that pair combination? T1 from upper half, T2 from lower half should be triggered at omega t is equal to alpha. Okay, this is the fundamental reason. Why do we need to trigger T1 T2 pair at omega t is equal to alpha? In the similar line, let us look into other two devices. Next, T3 is in common cathode configuration. Therefore, we can write T3 will forward bias when potential at B is greater than potential at A. That means B to A voltage is positive. B to A voltage is positive. Now, in the lower half, T4 is in common anode configuration. Hence, we can write T4 will forward bias when potential at A is less than potential at B. So, this means VBA is negative. Therefore, we should give firing angle to T3 when VBA is positive, firing angle to T4 when VAB is negative. If you look into the waveform, you can understand that VBA is positive and VAB is negative, that is in between pi and 2 pi. As per symmetric triggering sequence, T3 T4 pair should be triggered in between pi and 2 pi, that is at pi plus alpha. Okay. So the basic difference from midpoint converter to bridge circuit is, in midpoint converter at any instant either T1 or T2 were in conduction. But now here pair of devices were triggered. Instead of single device, pair of devices will be in conduction. Now in this particular circuit also we are assuming that load current is constant. Therefore, I can draw I0 waveform first. Okay, I0 waveform safely with a constant horizontal line. Okay, so what is the assumption for this? Load is assumed to be heavy inductive load in such a way that output current is having ripple free operation. In other words, continuous conduction. For load current to flow always, what is the requirement? Load should always connected to source. Okay, that is possible if you look into this circuit diagram. XY terminals will always connected in between source terminals A and B. That is possible. Now follow carefully here. X can be connected to A if T1 is on. X can be connected to B if T3 is on. Similarly, Y can be connected to B if T2 is on. Y can be connected to A if T4 is on, right? But as per the triggering sequence, we concluded that at a, alpha T1 T2 pair is triggered, 5 plus alpha T3 T4 pair is triggered. Therefore, in order to maintain continuous conduction, okay, T1 T2 pair is triggered at alpha. This pair has to conduct until next pair is started conduction. Okay, so in case of continuous conduction, in the previous circuit we told that SCR will turn off once next device or pair of devices started conduction. Therefore, as T1 T2 pair started at alpha, this pair will conduct up to 5 plus alpha, right? At 5 plus alpha next pair started conduction. Therefore, once T3 T4 pair started, T1 T2 pair will be turned off. Now T3 T4 pair will be in conduction from 5 plus alpha to next pair started conduction, that is 2 pi plus alpha. Therefore, conduction interval for these pair of devices, I am repeating again, alpha to 5 plus alpha, T1 from upper half, T2 from lower half will be in conduction. 5 plus alpha to 2 pi plus alpha, T3 from upper half, T4 from lower half will be in conduction. Okay. So before drawing the waveforms, first let us draw equivalent circuits so that it will give you more clarity to draw waveforms. Now let us draw equivalent circuits when these pair of devices are in conduction. So in order to draw equivalent circuit, follow this procedure carefully. It will give you very easy of understanding. So first draw the 4 devices with the open, okay, T1 T3 in upper half, T4 T2 in lower half, right? So this is the load, okay, and here there is a source, here there is a source, right? Now T1 T2 are on. So this is a T1 device, this is T2 device. What you can do? Close these 2 devices. Once you close these 2 devices, we can easily understand that X terminal is connected to source terminal A, Y terminal is connected to source terminal B, that is through T2. Therefore, what is output voltage? V0 is equal to VAB, because X is connected to A, Y is connected to B. This is V0 is equal to VAB. So in the beginning what I told, when you have a conclusions of VAB, then follow blue color sinusoidal. Okay. Therefore, alpha to 5 plus alpha, we can draw output voltage waveform like this. Alpha to 5 plus alpha, V0 is followed by blue color sinusoidal. Okay. So if you look into source voltage VAB waveform shape, cut that and plot here, it looks like this. Okay. Now what are the conducting devices? It is good to write down the devices numbers here. Okay. This is T1 T2 conduction interval. Now in the similar line, let us draw equivalent circuit for second half. Again here also draw the bridge circuit by opening all the 4 devices. After then, as per the subheading, we can close those 2 devices. Okay, and here this is a load, right, and this is a source voltage, this is a source voltage. Okay. Now, what are conducting devices here? T3 and T4. T3 and T4. So, you can close these two devices. On closing these two devices, then we can say that X terminal is connected to source terminal B through T3. Y terminal will be connected to source terminal A through T4. Therefore, we will have output voltage VBA because load is connected in between B and A terminals, right? This is what equivalent circuit from pi plus alpha to 2 pi plus alpha. Therefore, pi plus alpha to 2 pi plus alpha, what is output voltage conclusion we got? VBA. VBA means we should follow red color sinusoidal. Therefore, output voltage V0 will be same as that of red color sinusoidal. VBA is like this. Okay, that is from pi plus alpha to 2 pi plus alpha. Okay, pi plus alpha to 2 pi plus alpha. VBA. Next, after 2 pi plus alpha, again T1 T2 pair will be triggered. T1 T2 pair will be triggered. Hence, output voltage will be followed by blue color sinusoidal VAB. Okay, this is what output voltage waveform. And 2 pi to 2 pi plus alpha is same as that of 0 to alpha. Okay, so 0 to alpha you can write down the devices numbers T3 and T4. This is what output voltage waveform we can observe easily. This waveform also just similar to that of, not similar, it is the same as that of a midpoint converter. What is the only difference? Earlier only single device was in conduction at any given time, but now pair of devices are in conduction. Now just like midpoint converter, here also we should justify that line commutation process. In order to justify line commutation process, now observe carefully here. When T1 T2 pair is in conduction, I am looking into T3 T4, I am sorry, T3 T2, sorry, this is T4 only, sorry, T3 T4 voltage. Okay, now follow carefully. Anode for T3 is connected to B. Cathode of T3 is connected to A, right? Next, anode of T4 is connected to B. Cathode of T4 is connected to A. So, I can write down here, due to space limit, I am writing here alpha to pi plus alpha voltage across T3 and voltage across T4, okay, is equal to anode is at B, cathode is at A. I can write down here VBA, right? VBA. So, at alpha, if you look into the waveform, we can understand that VBA magnitude was negative. VBA magnitude was negative. So, what I can write here, that means T3 and T4 are reverse biased. T3 and T4 are reverse biased. So, basic idea is, in this bridge rectifier, whenever one pair, that is T1 T2 pair is triggered, immediately T3 T4 pair is a reverse bias. Next, if you see in the circuit diagram, total load current will flow through T1 T2 pair only. Therefore, we can say here current flowing through T3 and T4 is equal to 0. Current flowing through T3 and T4 is equal to 0. In the similar way, pi plus alpha to 2 pi plus alpha, what we can write down. So in this interval, T3, T4 devices are in conduction. Hence, let us look into T1, T2 pair. Okay, let us look into T1, T2 pair. So when T3 is on, I can say that B terminal will be connected at cathode of T1, anode of T1 is connected to source terminal A. Therefore, what is voltage across T1? VAB. Next, when T4 is on, source terminal A will appear at anode of T2. Therefore, what is anode to cathode voltage of T2? VAB. Okay. So, what we can say here, voltage across T1 and T2 is equal to VAB, right? Voltage across T1 and T2 is equal to VAB. Now, if you look into source voltage waveform, we can understand that at pi plus alpha, VAB magnitude was negative. What do you mean by that? Whenever T3, T4 pair is triggered, T1, T2 pair is a reverse bias. Let us write down that point. That is T1 and T2 are reverse biased. Okay. Next, what about current flowing through T1 and T2 is equal to 0. Now observe carefully, these are the two basic requirements for turn off process of thyristor or SCR, isn't it? Therefore, we can say that the turn off conditions were satisfied with respect to source property. There is no external circuit in order to create that. That is the reason in phase controlled rectifier circuits, commutation process is referred as line or natural commutation. Okay. Now by using those conclusions, what is the next waveform? That is voltage across T1 and T2 waveform. Okay, voltage across T1 and T2, right? So here this indicates that VT1 and VT2 both waveforms are just the same, right? Now, whenever T1 T2 pair is in conduction, voltage across T1 T2 will be 0. Next, pi plus alpha to 2 pi plus alpha, just now we concluded what is voltage across T1 T2, that is VAB. VAB means blue sinusoidal, right? VAB means blue sinusoidal. Therefore, you can draw blue color sinusoidal waveform here, that is just same as source voltage. 2 pi plus alpha onwards, again this pair is triggered, hence voltage drop will be 0. Now this is what voltage across T1 T2 waveform. 2 pi to 2 pi plus alpha will be same as that of 0 to alpha. Okay, 0 to alpha. Therefore, here this particular value is Vm sin alpha. Vm sin alpha. And what about this peak value? That is minus Vm. Minus Vm. Now from this you can easily identify that peak inverse voltage rating of devices will be Vm. In midpoint converter it was 2 Vm. In midpoint converter it was a 2 Vm. So that problem is eliminated here. Next point is circuit turn off time. Okay. So that is measured from pi plus alpha to 2 pi. Okay. So if you write down these conclusions, we can write it like this: peak inverse voltage rating is equal to Vm, which is same as that of the source voltage. Circuit turn off time is pi minus alpha. In other words, Tc is equal to pi minus alpha divided by omega in second. Okay. So this is what the expression for circuit turn off time. If you observe carefully, in midpoint converter also these two conclusions are same. Now the next waveform is voltage across T3 T4 pair. Okay. Procedure is same as earlier. 0 to alpha T3 T4 pair is in conduction. Hence, voltage across T3 T4 pair is a 0. Next, alpha to pi plus alpha T1 T2 pair is in conduction. Therefore, what is voltage across T3 T4? Just now we concluded that is equal to VBA. VBA means that is red color sinusoidal. Okay. So, if you draw the red color sinusoidal from alpha to pi plus alpha, it will be like this. Alpha to pi plus alpha, red color sinusoidal will be like this. Okay. So the same waveform will repeat periodically. Now in this case, we can have this peak value is equal to minus Vm. Okay. We can have this peak value is equal to minus Vm. And circuit turn off time can be measured from alpha to pi. Okay. Therefore, from this waveform again we will get same conclusions for PIV and circuit turn off time. Now with this I can have one important conclusion. Follow carefully. Earlier in the midpoint converter we have two thyristors. Now in the bridge converter there are four devices. Whether it is a 2 or 4 devices, as all the devices are working uniformly in that particular circuit, whatever circuit turn off time and PIV rating you are getting, those are applicable for remaining devices also. Okay. Therefore, going forward, when you have a more number of devices, okay, like 6 devices in 3 phase. So no need to draw voltage across all of the devices. It is sufficient to draw voltage across any one particular device, right? So whatever conclusions, generally those conclusions are circuit turn off time and peak inverse voltage. So those conclusions are applicable for remaining devices also. Therefore in the 3-phase rectifiers we will use this property. Okay. We will not draw voltage, no need to draw voltage across all the devices, any one device is sufficient. Now there is one more condition. Now observe carefully here, whatever output voltage waveform we have already plotted. So in this waveform I can notice that, see, pi by 2 or 90 degree is at this position, right? Alpha is before that. Therefore, we can treat this particular V0 waveform is applicable for alpha less than pi by 2. We can treat this particular output voltage waveform is applicable for alpha less than pi by 2. Okay. Suppose if alpha is greater than pi by 2, that is either 120 degree or 150 degree. What will be output voltage? We'll see. Okay. So I'm going to draw output voltage waveform for alpha either 120 or 150 degree. So here alpha is greater than 90 degree means alpha will be somewhere here, and pi plus alpha will be somewhere here. Okay. And 2 pi plus alpha is here. This is at 2 pi plus alpha. Follow carefully. I am drawing output voltage waveform for alpha greater than 90 degree. Okay. So basic concept is the same. What is that? Alpha to pi plus alpha, output voltage will be followed by VAB, blue color sinusoidal. Okay. So when alpha is greater than pi by 2, if you draw V0 waveform, that is blue color sinusoidal from alpha to pi plus alpha, it looks like this. Next, pi plus alpha to 2 pi plus alpha, we need to draw VBA, okay, VBA, where VBA is like this, okay. Next, 2 pi plus alpha onwards, this is how V0 waveform is. So we know that 2 pi to 2 pi plus alpha is same as that of 0 to alpha, and hence 0 to alpha output voltage waveform is a red color sinusoidal. So this waveform will give you one of the very interesting conclusion. Okay. Now follow carefully here. When alpha is less than pi by 2, my first observation is majority of V0 waveform is above x-axis. What do you mean by that? Area under V0 waveform is positive. This particular waveform will give you average output voltage as positive. Okay. Now in the second case, when alpha is greater than pi by 2, majority of V0 waveform is negative. What do you mean by that? Average output voltage is negative. So very important conclusions. When alpha less than pi by 2, average output voltage is positive. When alpha greater than pi by 2, average output voltage is negative. Now I may have one question here. This particular I0 waveform is drawn in the previous case. Can I consider the same waveform for alpha greater than pi by 2 also, or do I need to draw this particular waveform in the negative side? Try to follow carefully. In the beginning of rectifiers chapter, I told that whether diodes or SCRs will be used in this rectifier circuits. Under any conditions, load current will always positive because of unidirectional property of devices. Therefore, this particular I0 is applicable for alpha greater than pi by 2 also. Negative current is not possible. So let us write down all of these conclusions point by point so that it is very useful for understanding. Before that, first let us find out average output voltage. If you look into this particular wave, you can take any one waveform, either of these two, right? So periodicity is pi, and blue color waveform, let us integrate limits from alpha to pi plus alpha. Even if you take this waveform also, limits are from alpha to pi plus alpha. Okay. So let us write down these conclusions. Now all of these conclusions are based on output voltage waveform. Okay. Based on output voltage waveform. So what is average output voltage? 1 by pi, integration from, the limits are from alpha to pi plus alpha. The blue color sinusoidal is Vm sin omega t d omega t. Okay, that is what the integration. Therefore, in the previous midpoint converter also we had a same integration. In that case, we had a conclusion of 2 Vm by pi cos alpha. Okay, 2 Vm by pi cos alpha. Now remember carefully, this particular equation is applicable only for continuous conduction. Okay, so for full converter we will come across various situations. You should not use this equation for all situations. This particular equation can be used only for continuous conduction or constant current type of load. Now in this equation, let us write down the points one by one. If alpha is less than pi by 2. If alpha is less than pi by 2. So what is the conclusion here? Average output voltage is positive. What is the reason for that? Area under V0 waveform is a positive. Average output current is also positive. Again, what is the reason for that? Unidirectional property of the devices. Okay. Due to these two, we can write down here power delivered to the load, which is the product of V0 and I0, that is positive. So if power delivered to the load is positive, the direction of the power is from source to load, whereas the source is AC, load is DC. And hence I can write down here the direction of the power flow is from AC source to DC load. Very important property. Now, if alpha is greater than pi by 2, if alpha is greater than pi by 2, then V0 is negative due to area under V0 waveform is negative, but due to unidirectional property of the devices, output current is always positive. Therefore, we can say that P0, that is V0 into I0, is negative. Okay. So when the power delivered to the load is negative, means the direction of the power flow is from load to source, whereas load is DC and source is a AC. So we can say here the direction of the power flow is from DC load to AC source. Okay. Now we can put these conclusions in a more easy form of representation. That is, for example, in the converter characteristics, if we take I0 is on x-axis and V0 is on y-axis. Therefore, when alpha is less than pi by 2, what was the conclusion? Both V0 and I0 are positive, hence the quadrant of operation will be first quadrant. In this first quadrant, what was the conclusion we told? The power flow direction is from AC source to DC load. If you recollect our introduction lecture to converter analysis, at that time I told, if the direction of the power flow is from AC source to DC load, such a circuit is named as rectifier operation. Okay, such a circuit is in rectifier operation. Now, when alpha is greater than pi by 2, the direction of the power flow is from DC load to AC source. Okay, in such case, the circuit operation is called inverter operation, right? So phase controlled rectifier, especially this full converter, has very specific property. If alpha is greater than pi by 2, it is a rectifier operation. Sorry, if alpha is less than pi by 2, it is a rectifier operation. If alpha is greater than pi by 2, it is an inverter operation. Under this condition, that is when alpha is greater than pi by 2, under this condition, the circuit operation is known as line commutated inverter. Okay, line commutated inverter. Now, for example, if you consider load as DC motor, the first quadrant of operation is called forward motoring. Okay, forward motoring. Fourth quadrant of operation is called reverse regenerative braking, right? Reverse regenerative braking. If at all the load is a DC motor. What is a word called reverse? We'll discuss a little later. Now, especially in case of line commutated inverter, the power flow direction can be from negative to load to source. That is possible only when the load has dynamic element. Okay, load has dynamic element. That means it is possible for RLE type of loads only. Okay, so you can also say that that is a DC motor or separately excited DC motor. So these conclusions are based on output voltage waveform. Now, before going to next waveform, that is source current, first let us look into different directions. If you remember, while starting this circuit diagram, I have just shown this reference direction for IS. The reason is, follow carefully. The good practice for the network analysis is, in the beginning, it is preferable to give some directions of references for currents, polarities of references for voltages. During the analysis stage, if you get same as reference, treat them as positive. Opposite to the reference, then treat them as a negative. Okay, we'll follow the same thing here. That is very basic notation. Now, for example, if you look into the first equivalent circuit, when T1 is on, we know that a thyristor will carry the current from anode to cathode and hence give one arrow in upward direction like that. Now, if you follow that direction in the load side, I can draw the current direction something like this. Now, through T2, the direction of current will be like this, anode to cathode. So, in that direction, if you complete this circuit, we will get finally the directions of currents something like this. Observe carefully. This direction of current is same as that of source current direction, reference direction. Therefore, in this particular interval, we can treat source current is equal to plus I naught, same as that of the load current, but it is a plus I naught. Now, in the similar way, if you give the direction for this T3 anode to cathode like this, in the load side X to Y like this. Okay, this is I naught. T4 like this, anode to cathode. Now coming to source side, finally this is what the direction of currents in this complete circuit. Now observe carefully, one of the important point is source current is, now see this direction, this is opposite to reference direction. What do you mean by that? We should take this current as negative. Is is equal to minus I naught. Okay, Is is equal to minus I naught. Now, in order to draw the waveform, what is the conclusion? In what way you need to draw? Alpha to pi plus alpha, Is is equal to plus I naught. Pi plus alpha to 2 pi plus alpha, Is is equal to minus I naught. Therefore, I will just put those conclusions in the waveform here. 0 to alpha, T3 T4 pair is in conduction, hence we can draw source current here is equal to minus I naught. Okay, alpha to pi plus alpha, source current is plus I naught. Okay, it will change from minus I naught to plus I naught. This is plus I naught. Next, pi plus alpha to 2 pi plus alpha, the source current is minus I naught. Source current is a minus I naught. Now 2 pi plus alpha again plus I naught, that waveform will repeat. This is what source current waveform. Okay. Now observe carefully, what is the reason to start full wave rectifier? In half wave rectifier circuit, source current has DC component. Source current has DC component. Therefore, we told that in half wave rectifier circuit there is a problem of source transformer saturation issue. In order to overcome that, we told use multiple devices in such a way that DC component of source current is 0, right? Now observe carefully, positive area and negative area both are equal. As per Fourier analysis, A naught by 2 term is 0. Therefore, you can say this particular waveform source current is DC component in source current is equal to 0. There is no source transformer saturation issue. But source current is not a sinusoidal waveform. Okay. If you remember or if you recollect from the beginning lectures, I hope lecture 2 or lecture 3, in that exactly for the same waveform we did Fourier analysis. We did Fourier analysis. For this particular waveform, if you recollect and draw fundamental component, it will be something like this. Fundamental component started from omega t is equal to alpha. The instant where this square waveform started, x-axis. This angle is alpha. Okay. Now, what is the peak value of this particular waveform? 4 by pi multiplied with I naught. 4 by pi multiplied with I naught. Okay. So, interesting properties of this source current. Now, let us write down all of these properties one by one. Source current waveform. All of these conclusions are based on this. Source current waveform. Okay. Source current waveform. Now, first point is source current is a square waveform. Source current is a square waveform on the assumption of, by assuming load current is equal to constant. Right? By assuming load current is equal to constant. When the source current is a square waveform, we can say that DC component in IS is equal to 0. DC component in IS is equal to 0. What do you mean by that? There is no saturation problem. There is no saturation problem in source transformer. There is no saturation problem in source transformer. Now, by recollecting our beginning lectures, we should write Fourier series equation for source current something like this. Sigma odd numbers of n. This particular harmonic analysis is very important for GATE exam. Not only GATE exam, any PSU also you will get conclusions based on these harmonic discussions. Sigma odd numbers of n, 4 I naught divided by n pi sine of n into omega t minus alpha. Okay. So what I can say here, source current contains all odd harmonics. Source current contains all odd harmonics. What are all those harmonics? 3, 5, 7, 9 and so on. Third harmonic is the lowest. Third harmonic is the lowest harmonic. Okay. Next one is what is RMS value of fundamental source current? I suffix S1. S indicates source current and 1 indicates fundamental component. Peak value of fundamental sinusoidal current is 4 I naught by pi, whose RMS value can be written as peak value divided by root 2. Then it can be expressed as 2 root 2 by pi into I naught, where 2 root 2 by pi numerical value is 0.9. Next, let us write down RMS value of source current. In the basics lectures, we discussed that for a square waveform, RMS value is equal to magnitude. At the time we told in the converter analysis, we can use all of those conclusions. Okay. So RMS value of source current is equal to I naught. RMS value of fundamental source current is equal to 0.9 into I naught. Now here, observe carefully. I will show you two waveforms. Okay. One is a sinusoidal V, and let me take here omega t, here also omega t. Okay. And there is one waveform like this. Let me take, this is a current waveform. Okay. Now, for example, I have this angle is a phi. Now, the basic question here, what is the phase angle between voltage and current waveforms? Can I write this is equal to phi? Okay. Answer is no. You should not define phase angle between V and I in this particular case. Current waveform is a non-sinusoidal. Whenever you are defining a phase angle between two waveforms, both should be of sinusoidal nature. Okay. Or one is a sine, other is a cosine is also fine. But both should be of sinusoidal and having same frequency. Here, current waveform is a non-sinusoidal. Therefore, you should not define phase angle between one sinusoidal and one non-sinusoidal. Whenever we are not able to define phase angle between V and I, whatever the definition we will use, generally power factor is equal to cos phi, this definition is not applicable. Okay, remember carefully, power factor is equal to cos phi, this is applicable only when phi is available. When phi will be available? Only when voltage and current are sinusoidal. That is nothing but only when voltage and current waveforms are free from harmonics, then only phi is available. Okay. Therefore, power factor is equal to cos phi formula is applicable only for harmonic free environment. Only when voltage and current waveforms are free from harmonics, in that case you can use power factor is equal to cos phi. But whether harmonics are present or not, power factor is equal to basic definition active power by apparent power. Okay, active power by apparent power, or you can also write kW by kVA or MW by MVA. So you can use any one of these definitions. Whether harmonics are present or absent, these definitions are applicable. But power factor is equal to cos phi, that is one subcategory of power factor definition. This is valid only when voltage and current are harmonic free. But what is the reason to discuss all of these things in power electronics subject? Because that is what our present situation. Our source voltage waveform is pure sinusoidal, but source current is non-sinusoidal. Source current is a non-sinusoidal. Therefore, power factor at input side, you should not simply define power factor is equal to cos phi. Okay. Under that condition, how to calculate power factor for a rectifier circuit? There is a different procedure. Let us do it one by one. Now here, when source voltage and source current both are not sinusoidal, okay, means here source voltage is sinusoidal, no need to worry about it, because our rectifier analysis has started with by assuming source voltage is pure sinusoidal. So what is the point here is, when Vs is sinusoidal, Vs is a sinusoidal and Is is non-sinusoidal, then IPF can be calculated, as follows. Okay, input power factor of the rectifier can be calculated as follows. Now, what is the first thing we need to calculate? That is DPF. Okay, DPF. I will tell you what is the full form of DPF. Here, source voltage is sinusoidal. Source current is also fundamental component of source current is also sinusoidal. Therefore, we can define phase angle between fundamental source voltage and fundamental source current. That phase angle is represented with phi 1. Phi 1 is angle between fundamental source voltage and fundamental source current. If we take cos of this phi 1, then that is called DPF. Okay, DPF. Full form of DPF is displacement power factor. Also called fundamental input power factor. Okay, fundamental input power factor. So, in case of rectifier circuit, you should not calculate input power factor simply saying cosine of phase angle between source voltage and source current, because source current is not a pure sinusoidal. Okay, next. The second factor that we need to define is displacement factor. Now, displacement factor will be defined at AC side. Okay, while starting the rectifier analysis, we discussed AC and DC waveforms comparison. Displacement factor, distortion factor. Sorry, this is a distortion factor. So, this distortion factor to be defined at the AC side, but source voltage is sinusoidal. So, we need not to define distortion factor for voltage waveform. You have to define only for source current waveform. What is the definition for this particular function? DF is equal to IS1 divided by IS. In our earlier definition, I told X1 by XR, right? So here, distortion factor should be defined at AC side. AC side, there are two parameters, source voltage as well as source current. As the source voltage is pure sinusoidal, no need to define distortion factor for Vs. So you have to define only for Is. So distortion factor, you can also say in input current or source current. Some authors used to use that current distortion factor, CDF, whatever the way, just a symbol. Concept is distortion factor, RMS value of fundamental source current divided by RMS value of source current. If you substitute these values, what can I write in the numerator? 2 root 2 by pi into I naught. Denominator is I naught. Okay. So I naught and I naught can be cancelled. Therefore, it will give you 2 root 2 by pi, whose numerical value is 0.9. Okay, 0.9. Next. So by using this, we can define input power factor. So what is the basic definition we discussed earlier? Input power factor, power delivered to the load divided by source volt ampere. Okay. So what is P naught here? V naught multiplied with I naught divided by Vs into Is, right? Vs into Is. So substitute these values. What is V naught? 2 Vm by pi into cos alpha multiplied with I naught. This is in the numerator. Okay. This is in the numerator. What is in the denominator? Vs, RMS value of source voltage, that is Vm by root 2, and Is is equal to I naught. Okay. So we can cancel I naught and Vm here. What is the simplification here? Input power factor is equal to 2 root 2 by pi multiplied with cos alpha, right? In other words, 0.9 into cos alpha. 0.9 into cos alpha. In other words, 2 root 2 by pi or 0.9, we can write it as a distortion factor multiplied with cos alpha, that is a dPf. Okay, fundamental input power factor or displacement power factor. This is the definition for input power factor. Very, very important conclusion. Observe carefully. Input power factor is less than displacement power factor. Why? What is displacement power factor? Cos alpha. Distortion factor value is 0.9. It is less than 1. The main reason for dF is to be less than 1 because RMS value of fundamental source current is not the same as that of RMS value of a source current. That is due to non-sinusoidal nature of source current. That means source current has odd harmonics. What is the impact of input current harmonics or source current harmonics? Important word, issues of line current harmonics in the syllabus. Because of source current harmonics, distortion factor is less than 1. Due to that, input power factor of the rectifier circuit is reduced. That is why I highlighted this point even in the introduction class also. Phase controlled rectifier circuits, input power factor is less when firing angle increases. If you increase alpha, input power factor will further decrease. So why do you need to worry about input power factor? Because input is a power system grid. When phase controlled rectifier is operating with alpha increases, power factor grid will deteriorate. Power factor of the grid will be deteriorated. That is the basic drawback of phase controlled rectifier. Now can you tell me when IPF is equal to DPF? If IS1 is equal to IS. For IS1 is equal to IS, waveform should be pure sinusoidal. Waveform should be pure sinusoidal. Therefore, at the source side, filters are required in order to eliminate the harmonics. Okay. So in phase control, this full converter circuit, input power factor is less than fundamental power factor, that is due to presence of source current harmonics. Very, very important conclusion. Now there is another property of source current. What is that? In the beginning of the rectifier chapter I told, whenever you have AC waveform but it is a non-sinusoidal, you have to define two factors. One is distortion factor, another is total harmonic distortion. Anyhow, distortion factor we have already defined, that value we got 0.9. Now let us find out THD in source current. THD in a source current. The common practice is to express in percentage of THD in source current. Remember carefully here, percentage of THD in source voltage not required. Why? Because source voltage is pure sinusoidal. For pure sinusoidal waveform, total harmonic distortion will be 0. No need to calculate separately. So percentage THD, total harmonic distortion. How can you define this? IS square minus IS1 square divided by IS1 into 100 under root IS square minus IS1 square divided by IS1 into 100. Okay, so if you substitute IS value, that is I0 and I0 into 0.9 whole square, that is IS1 under root divided by 0.9 into I0 multiplied with 100. Okay, so if you calculate this value, we will get, let me write down clearly, very important conclusion. Percentage THD in source current, you will get this value as 48.43%. 48.43%, right? Now we can also express THD in a different way, percentage THD, or let me write down simply THD. Okay, THD is equal to under root, suppose if you pull that IS1 inside the root, we can write it like this, root of IS by IS1 whole square minus 1. This will give you under root 1 by df whole square minus 1. 1 by df whole square minus 1, total under root. Now if you substitute df, what is df we got? 2 root 2 by pi, reciprocal and square it. Then you will get pi square divided by 8 minus 1. THD is equal to root of pi square by 8 minus 1. This is about THD. Okay. Now there is another way of representing this input power factor THD. So suppose if you write input power factor expression, what is that? DF into DPF, right? Now just for reference, THD is equal to square root of 1 by df whole square minus 1. So df can be expressed in terms of THD, and you can rewrite this IPF like this, dpf divided by root of 1 plus THD whole square. Okay, IPF is equal to dpf divided by root of 1 plus THD whole square. So these are the basic or important relationships, especially see these relationships not only for full converter, for rectifier circuits these definitions will be applicable. Okay, now all of these formulas or discussions are based on the source current. Now there is one more waveform. Now the next waveform is waveform for any one switch current, your wish. Let me take T1 for reference. So we have equivalent circuits from alpha to pi plus alpha and pi plus alpha to 2 pi plus alpha. Now you tell me from where to where T1 device was in conduction. I can say that alpha to pi plus alpha. Therefore, let us draw T1 current waveform from alpha to pi plus alpha. How much current that is flowing through the device? That is I0. Therefore, we can draw T1 current waveform is I0 from alpha to pi plus alpha. Similarly, the same waveform will continue after 2 pi plus alpha. Okay, the simple waveform. With this, waveforms completed for this particular circuit. Now, based on this SCR current waveform, two factors I would like to calculate. One is average value of thyristor current. What is that? Area or rectangular waveform. Recollect our average and RMS values lectures. I naught multiplied with pi is the area divided by one cycle time, that is 2 pi. Hence, average value of thyristor current is equal to I naught by 2. Next, RMS value for this device current, IT RMS. For the rectangular pulse, how can you write? Magnitude square multiplied with pi divided by cycle time under root. Okay. So this will give you I naught divided by root 2. So RMS value of thyristor current is equal to I naught by root 2. Average value of this thyristor current is equal to I naught by